to you about geoengineering, which is one of the possible ways of getting us out of the problems we're in with climate change. But I want to make it very clear, I don't think this is the best way. I think it's probably close to the worst way, but given the slowness of some of our political leadership, it might end up being the only way. So just a little about me. I taught at university in physics department for 30 years. I also teach for WEA. I've done research in atmospheric science for 40 to 50 years, particularly in the areas of atmospheric radiation, which means the flow of visible and infrared radiation through the atmosphere, and the role of small particles in the atmosphere. I spent time working for NASA, the University of Arizona, the Los Alamos National Laboratory, and I've also co-authored a quite senior level university textbook on this subject. So let's start at the beginning. The Earth's climate is maintained by a balance, an equilibrium between the inflow of solar radiation, which we call shortwave, and the outflow of terrestrial, sometimes called infrared radiation. The more technical term is long-wave radiation. Now, the outflow is determined by the surface temperature of the Earth and the composition of the Earth's atmosphere. And the Earth's temperature, surface temperature, is always going to adjust to make sure there is a balance. So it will move up or down as required. And over geological time frames, these parameters have changed. And the Earth's atmosphere has always adjusted. But invariably, these changes were much slower and always more natural. Today, as we know, things are rather different. So now here is a cartoon of the greenhouse effect. It's a nice cartoon, but it's a little inaccurate. So on the left, it shows sunlight coming in, some of it coming all the way through to the ground, roughly 50%, and about 30% being reflected by the atmosphere, particularly clouds, and by the land surface, such as ice sheets and deserts. The remaining 20% is absorbed mainly by water vapour in the lowest kilometre of the atmosphere. On the right, we see infrared, also called long-wave radiation, making its way back out to space. Most of this is actually absorbed by the atmosphere. The diagram suggests it's scattered. That's not the case. It's absorbed, but then re-emitted. And a lot of the re-emission comes back down to the ground, which makes the surface warmer than it otherwise would be. The reason that absorption and re-emission is different from scattering is that the re-emission depends on temperature. Scattering doesn't. Okay, to have a stable climate, clearly we need stability of these radiation fluxes. And through the Holocene, for the last roughly 11,000 years, this has been the case. If, for any reason, there are changes in these fluxes, then this is referred to as a radiative forcing, because we're changing the radiation balance. In general, this will lead to a climate change. But if we quantify this fact, or if we would like to, we need a full-scale climate model, which is a glorified weather model. So, for example, if we increase greenhouse gases, this will trap more of the outgoing long-wave radiation, less will escape to space. The planet will have to warm up to push more out. So the planet will warm, and this is called a positive forcing. If we have an increase in the reflectivity, better known as the albedo, for example, increased scattering by either the surface or the atmosphere. This would mean less energy coming in. This would be a negative forcing and would probably lead to a planetary cooling. As I said, the details, quantification requires a very large model. But these basic principles are all fundamental and incontestable physics.
But currently, as we know, the Earth is warming because there is an imbalance. There is less radiation going out than coming in. The difference is it's probably a bit less than a watt per square metre. Roughly a watt per square metre, probably a little less. And this is because of the rising levels of CO2 and the other gases. An important point that more than 90% of this excess energy is going into the oceans. And some goes to melt the ice sheets, and somewhere between 1% and 3% warms the atmosphere. Now that's a sobering thought. Just think if it was all going into the atmosphere. But what this also means is if we stopped emitting greenhouse gases today, the Earth will still continue to warm because of this imbalance. So maybe 3/4 of a degree, but don't quote me on that. However, there are other ways to correct this imbalance, and they are referred to as geoengineering. So geoengineering is also called climate engineering. And according to the Royal Society, it's the deliberate large-scale manipulation of the planetary environment to counteract anthropogenic climate change. And there are two main avenues. Carbon dioxide removal, which is certainly the better option, looks for ways to remove CO2 from the atmosphere or the system. Solar radiation management, which is what I'll be talking about, tries to rebalance the equation by reflecting sunlight back to space so that the incoming balances the outgoing. Now, mitigation is obviously what we aim for, but one day we may need some of these ideas as an emergency. So let me start by looking at the CO2, the carbon dioxide removal. Now, if we're to remove CO2 from the system, this requires energy because we burnt coal to release heat, to release energy. So if we want to convert CO2 to some other form of carbon, that's going to take energy. Some fanciful ideas have been put up and they should be pursued, but I'll leave them for now. And we also need to understand that taking it out of the atmosphere is challenging. It's more difficult than carbon capture and storage from a power station. So if we look at photosynthesis, all this energy comes from the sun. So it's free, as we know. That's why we talk about solar energy. But it's quite diffuse. But we could exploit this by growing special crops, perhaps genetically modified in some way, harvest them, burn them as biofuels, or, and please don't quote me on this, we could wrap them in plastic and dump them in the ocean. It's one way of getting rid of carbon. Soil carbon is important, but there are a lot of issues and uncertainties around the stability of this. It may work, but as I say, there's still much to be learnt. There's another obstacle with carbon dioxide removal, and that's what's known as the rebound effect. Of the CO2 that we put into the atmosphere, maybe half stays into the atmosphere maybe 40% into the ocean and 10% taken up by vegetation. It varies a lot year to year. But what this means is only about half goes into the atmosphere. And there's this equilibrium exchange across the ocean surface, depending on where there is the greater concentration. And so CO2 will flow from one to the other. So if we remove any CO2, there'll be a backflow. So what that means is if you decide you need to remove a gigaton, you're going to really have to remove 2 gigatons. That also means, of course, if we can remove CO2 from the ocean, some will flow from the atmosphere into the ocean, which will be good. Now, perhaps we can improve phytoplankton growth by adding nutrients such as iron. However, there are other nutrients that are needed. Now, some of this plankton will die and sink to the ocean floor and take the carbon down with it, removing it permanently from the system. We call this ocean fertilization, and we can see it whenever there's a big dust storm that carries desert dust out to sea, like the great Sydney dust storm. I had a graduate student working at the time, and he did some very quick work to look for this. I know some people who have just taken a boat out to sea, thrown a bucket of iron filings over the side, see what happens. It works, but it's probably not the best option. We could farm algae and kelp, again, perhaps GM, and bury it. That would possibly be a more manageable exercise. However, all of these ideas at the moment don't look like they're going to do enough to remove enough CO2 quick enough. That is to say, we can't remove it as quick as we're putting it into the system. However, long term, there's a different question. Many scientists are comfortable with the 2-degree target. And the reason they're comfortable is they can't see anything happening better than that. That's our best hope. 1.5 degrees is pie in the sky. But there are some, Jim Hansen and Stefan Rahmsdorf, they point to evidence from sea levels in the past, say about 130,000 years ago. The temperature was 2 or 3 degrees warmer than today. Sea level was maybe 5 meters higher. So what they're concerned about is if we get up to 2.5 degrees and hold at that point, slowly the ice caps will be eroded by these warmer and expanded oceans and gradually eat away at the ice sheets and raise the sea level. So even if carbon dioxide removal isn't a short-term answer, it may be worth pursuing in the decades ahead to just draw CO2 back out of the atmosphere to get us down to maybe where we are today. All right, let me turn now to solar radiation management. So here we aim to reduce the incoming solar radiation. That is, we increase the Earth's reflectivity. The technical word is the albedo. So we could paint all the roofs white, particularly in the tropics where they get more sunlight. It's a big ask. They're going to get dirty quickly in polluted places like India. And at best, we might achieve 1/10 of what we need. Could we replace native grasslands with lighter genetically modified species? On this theme, I was in a conference in Perth back in early February, and someone was suggesting, southwest of WA is a big wheat growing area. What if they could use a strain of wheat that had a higher reflectivity? Might it produce some local cooling? Then, of course, there are questions on water use, biodiversity, and even the carbon cycle. Orbiting space shields. This is one of those fascinating ideas. You could put up these satellites that could unfurl a 10-kilometre wide sail. It'll stay there because there's no air to get in the way, and each time it passes in front of the Earth, it'll block a bit of the sunlight. You'd need quite a few of them, obviously. But the major focus is on using pollution to fight pollution. So let me take you through some science. Aerosols. Now, this is my sort of area of specialty that I've worked at one way or another for 45 years. So aerosols, or particulate matter, is the word we use for particles, droplets, mixtures in the atmosphere. And they can be from 10 nanometers or less up to 10 micrometers and more. Down at the bottom end, well, are they molecules, are they particles? Bigger than 10 microns, they usually settle out fairly quickly. Now, they have a lifetime in the atmosphere of 4 to 7 days, typically, so they're not well mixed around the globe. So this is a challenge for science to try and measure and understand their properties and how they vary across the globe. And some of my friends at NASA have worked on this for many years. Primary aerosols, such as desert dust, sea salt, and soot, they're particles that go directly into the atmosphere. And mostly these are large particles, with the exception of soot, which starts off very small. Secondary aerosols are the more interesting. They're produced by chemical reactions in the atmosphere, and in particular photochemical reactions, needing sunlight to convert gases to less volatile substances, which then condense to form particles and grow. So the best example is sulfur dioxide. Whenever we burn a dirty fuel with sulfur in it, sulfur dioxide is emitted. It's converted to sulfuric acid. When I was at school, my teacher said no one knew how. It probably wasn't true, but when he was at university, it probably was true. It's a complex process involving sunlight that gets converted to sulfuric acid, and then that will react with something like ammonia to form ammonium sulfate aerosol. So aerosols play 4 very important roles in the atmosphere. They're a very important part of the whole of atmospheric chemistry because all sorts of reactions take place on particles and inside particles. Let me give you an interesting example. Sea salt emitted from the oceans. Let's suppose that sodium chloride is carried on land by onshore breezes into the plume of a power station where the sulfuric acid is being produced. That sulfuric acid will react with the sodium chloride to produce sodium sulfate and hydrochloric acid. So this is part of the chemical nature of what's going on in the atmosphere. Very important is that every cloud droplet has a little aerosol particle inside it. If the air were perfectly clean with no natural or anthropogenic aerosols, we could never form clouds, even at several 100% relative humidity. Water can't condense on nothing. Aerosols are also very efficient light scatterers, especially when their size is about the same size as the light that's hitting it. So in the case of sunlight, if they're around, say, half a micron in size. Finally, as we probably know, they're a major contributor to air pollution with maybe 5 million deaths a year caused directly or indirectly by particulate pollution. So this just shows the contribution in the red, I hope you can see it, of the greenhouse gases in terms of their radiative forcing, about 3 watts per square metre. But the aerosols are mostly doing a cooling. You know, there's a very small probability that the soot and the desert dust which absorb are outweighing the scattering, but almost certainly that's not the case. So when we add the two together, we see that the total forcing that humans have produced over the last century or so is about 2 watts per square metre. Now, the Earth is warmed up by a degree, and that's why the current imbalance is only about 1 watt or a bit less. But that just shows the relative importance of the gases and the aerosols. Stuff that goes into the stratosphere will typically stay there for a year or two. Now, I'm not talking about the ash clouds that you see on TV. I'm talking about the sulfur gases, which produce sulfate aerosols, sulfuric acid. Mount Pinatubo cooled the Earth for about 0.4 of a degree for a year or two. It was the first serious test of our climate models because they were just at the point where we could have some confidence in them. So, question, could we put aerosols or sulfur gases or something into the stratosphere to reflect sunlight back to space? Now, because of a lifetime of, let's say, a year, we'd need to keep doing this. And if we do this at low latitudes, well, there's more sunlight to scatter. But it's been estimated that 10 megatons of sulfur every year might be enough at a mere several $100 million. Now, Elon Musk could do that. Donald Trump's tax bill, which he hasn't paid, is probably of that order. Clive Palmer's advertising at the last election. I mean, there are plenty of people who could do this. It's not expensive. The other option is to try and do something about clouds. As I said, every cloud droplet has an aerosol particle in it. So let's imagine we introduce some more aerosols into a region of space where a cloud is forming or is about to form. Now, thermodynamics, temperature, tells you how much water is going to condense. That's simple. But then that water will look for particles to condense onto. So if you have more of the right type of aerosols, you'll get more but smaller droplets. Same total amount of water, but smaller but more droplets. Now, simple physics shows that a cloud like that is more reflective. This is actually known as the Toomey effect. Sean Toomey was the person who discovered it, and I had the enormous pleasure of getting to know him when I was at the University of Arizona. Wonderful guy, great Irish sense of humour, and he loved the Melbourne Cup. He'd spent some time here in Sydney. There are also reasons for believing that these clouds will take longer to precipitate, because if the droplets start off smaller, it'll take longer to grow big enough. So brighter clouds, longer-lived clouds, that should be a negative forcing. Is there any evidence for this? Well, these are ship tracks. Each one of these bright streaks is where a ship has sailed under these clouds, emitted its dirty pollution from, marine diesel is the worst shit on Earth, and that's gone up into these clouds, and these trails are where the cloud has been brightened by the sulfur stuff that's come out. The reason why they're jerky is simply the moving of the cloud, nothing more. So could we do this one? Well, the logical thing is to pick clean clouds because there a small increase will have a bigger effect. If there's already a lot of aerosols there, so the clouds are already reasonably bright, but if you go to clean clouds, such as over the Southern Ocean or South Pacific, then they might be the easiest ones to brighten. It's also been suggested by some people I know at a couple of the Queensland universities that we might try to pump aerosols of one sort or another into clouds that are being drawn across the Great Barrier Reef by the trade winds and try and cool down the Great Barrier Reef to stop the issues up there. The biggest problem with that, of course, is the clouds keep moving. So this is more a global than a local phenomenon or idea. But again, the increase would probably only be modest. What about some of the drawbacks, the imperfections? Well, the first thing is solar radiation management, in the absence of mitigation, would allow CO2 emissions to keep going up, and so that allows ocean acidification to get worse. So clearly carbon dioxide removal is what we want, but it does seem to be harder to achieve. Stratospheric aerosols, which I'll talk about some work on that in a minute. What about when that stuff comes down to Earth? Are we going to be rained on by sulfuric acid? Well, I mean, the answer is yes, but we already have this when volcanoes like Pinatubo go off, and the effects are negligible compared to all the other sulfur gases in the atmosphere. So that's not a concern. A bigger concern is that the ozone hole contains within its physics and chemistry a number of chemical reactions that take place on the surface of what are called polar stratospheric clouds, small aerosol particles, particularly ones known as NAT, which stands for nitric acid trihydrate. So if we put more aerosols up there, the ozone hole is probably going to be with us for longer. If we're scattering sunlight back to space, it might have an impact on photosynthesis, probably small because a lot of the scattered light still gets scattered down to the ground, but focused solar collectors would suffer because there's more diffuse light, less direct light. So let's turn to questions beyond the science. Can we do it? Should we do it? Should we even investigate it? Well, let's start with the simple moral questions. Do we have the right? Do we own the planet? Well, I think we know the answer to that, and it's no. But since we're already making a mess of the planet, is it okay to try and undo our damage? That's actually a PhD in philosophy, I think, to answer that question. Could geoengineering be an excuse to carry on with business as usual? Might the coal companies pour money into research in geoengineering and hope that they can keep going? And what happens if all that money is poured in and we can't solve the problem? Should we do the research but keep it secret? Well, it's already been discussed by the IPCC, so that's a little bit late. On the other hand, if we see something dangerous springing up, like a threat to the Greenland ice sheet, something that we could ramp up very quickly, maybe just what the doctor ordered. Governance is an interesting issue. We clearly need open disclosure, and we need three teams. One that's proposing and doing the research, an independent team to assess the results, because researchers, we're human, we can see the best in our results and miss bits and pieces, so an independent team. But we need a third one to monitor what's going on, and if they see something nasty happening, to say, stop, absolute stop. So this is what has been proposed by Oxford, that is regulated as a public good, public participation, disclosure and open publication, independent assessment, which is basically two of these teams, and governance ahead of deployment. Now, the UK House of Commons had a select committee looking into this. I was actually asked to make a contribution. I was on a cruise around New Zealand about 10 years ago, 8 years ago. It's interesting timing, since a cruise around New Zealand was the Corona Princess. I wasn't on that ship, but it was the Princess Lines. What about weaponization? Could we damage enemy agriculture? Quite possibly. Or modify a battlefield to favour weapons of one side, such as maybe laser-guided weapons. When I was at Arizona, I must have met a guy at a conference, and he worked at White Sands Missile Range. So he sent me a bunch of reports titled The Aerosols of Central Europe. And I wondered, what on earth does White Sands Missile Range want to know about the aerosols of Central Europe? Then someone pointed out to me one of the scenarios for the start of World War III was a mass tank attack through the Fulda Gap in central Germany. There are two ways to stop a mass tank attack. One is laser-guided weapons, and the other is battlefield nuclear weapons. I think I know which I prefer. There is also this convention on the prohibition of military use, but this just highlights it doesn't eliminate the risk. Hitler signed a non-aggression pact with Stalin, and he scrupulously obeyed it until the day he didn't. So all these treaties are as valuable as the paper they're written on. Let me now turn in the last few minutes to what Harvard is doing. So I've taken a lot of this, simply lifted it from their website. There's a very good 8-minute video with some of the key people talking about why we need it, what projects they're planning, etc., including these delightful words: solar geoengineering is terrifying, but not doing it may be worse. So again, from the website, a lot of the money is not coming from granting agencies like NSF. It's coming in from their own in-house funding. So that's a good thing, I think. The website then lists 8 projects. I'm going to focus on the 2 which are science. And then there are 5 other moral, policy, political projects. And finally, an overview project which basically says, in all the other 7 projects, is there anything we still haven't thought of? So they're very serious. So look, I won't read all of this. By the way, I'll send someone a PDF of this to distribute to all of you. So the first project is a whole lot of laboratory research. They're planning on putting some stuff up into the stratosphere. So that particular approach. So they want to look at all possible candidates and look at all the possible risks, all the possible harm that they could do to the ozone layer, to the temperature of the stratosphere, which affects its circulation, and when the particles fall out, what effect might it have lower in the atmosphere. So they want to look at everything they possibly can to rule out any ones that don't seem to qualify and just leave those that pass. That doesn't mean they're perfect. It just means they've passed the tests that they can think of. Then they plan to put some stuff up into the stratosphere to see if it can do the job of reflecting sunlight without causing harm to the ozone layer or the temperature profile. Let me focus on this. What they plan to do once the laboratory work is finished is send up a balloon, a balloon platform with some kind of propulsion and injecting less than 1 kilogram of stuff at about 20 kilometres, and that will produce a plume, because the wind will carry it, with a length scale of maybe 1 kilometre and a diameter of a couple of 100 metres, and then the balloon will fly through that to measure what's happening, to learn everything that can be learnt, so that they can improve the science, improve their modelling before ramping up to the next scale. Then there's a couple of others now, I'm not sure. Okay, look, just before I hand back to the chair, I've got a couple of upcoming Zoom presentations for WEA in Science Week on past climates and on climate variability. And then my big course, which I'm not going to do by Zoom, only if we can do face-to-face, which covers everything you'd ever want to know about the atmosphere and its environment. Very quickly, it covers all those 8 topics.
Thank you for watching. Please subscribe to our CCL channel by hitting the button in the top left-hand corner of this screen. Spread the word of CCL by using the share icon to as many of your contacts as possible. Thank you. See you next video.